Okay, today I will talk about one very interesting phenomenon of the neutrino physics, which is called the radiative emissions of the neutrino pair. Briefly, it's RENP. This is some of the ones very interesting phenomena of the neutrino. The neutrino might be emitted from the atomic system. So in the atomic system, there are excited states and the grounded state. And usually is when the photons transit from the excited state, the ground state, the photons are emitted. But the electrons are transit from the excited to the ground state. But such a photon emissions can be possible by the QED attacks. But if we consider additional weak interactions, then the neutrino pair can be emitted. So this is a weak interaction pair. So the W boson and Z boson is the mediated by converting between the electrons and neutrino as a charges current and the neutral current. So such a second sort of weak interactions vertex require the additional intermediate state P in here. So there's such a radiative neutrinos of the radiative emission of neutrino pair RENP. We want to observe such RENP photon signal. So our goal is observations of such a photon instead of the observation of the neutrino, because neutrino detections that requires large volume detectors. So we want to reject the other QED transition signal. This is a background. So other possible QED signal is the first example is the E1 transitions. The E1 transitions mean that we want to choose the excited and the ground state such that such E1 transition is forbidden. So the difference of the total angular momentum should be the 2. So there's one example in the general atom for the excited state with such orbital notations and the ground state, like that, and the intermediate state P. And for the excited, for the given excited and ground state, another difference is given by the almost 8.32 electron volt. And there are also the another difference between the intermediate excited state. This another difference can be obtained from the atomic spectral database of the NIST. So there is some corresponding wave length here, and the orbital notation for the channels. And next, also we want to reject the two photon emission process. This is E1 times E1 transition, such as two photon emission is called the TPE, the two photons emitted, and this is the main background of the RENP. If we reject the E1 transition signal by choosing some specific excited and ground state. And we will make some compensated atom, and the light from such a compensated atoms is proportional to the pace of the emitted particle. So this one, pace of the emitted particle. So the light, and this is a pace factor, and the momentum conservations, and there are amplitude as asymmetrics. And the number of stratoms are here. So this is a lattice with the condensated stratum density, and this emitted particles mean that in this case the two photons corresponds here. This is called the macrocoherent amplifications. By using such a condensated stratoms and its property, we can reject such a main background TPE. For example, for the cylindrical target, such a TP process is only occurs at the near axis. So the light or the E1 times E1 are non-zeros at the theta equal to 0 and the pi. So theta equal to 0 and also theta equal to pi from this macrocoherent amplifications with this phase factor. But in the case of our goal, our signal lamp has a wide angular distribution. So the two other lamp signals comes from the other wide angles in here. So we can measure the lamp. So this is the near axis directions from the two photon emissions. the figures are taken from this paper. So the TP background can be rejected by the setting the detectors on the outer axis. So the lamps, the signals that comes from the other axis here. So this is a lamp signal, and the TP background only is considered this near axis, so that we can set the detectors at the outer axis here. And also there might be the high order QED transitions, but the energy range of such a high order QED processes are different from the lamp. So for example, we can plot the light at the energy of the emitted photon. So for example, the lamps the spectrums are like that, but the other energy distribution for the such high order QED transitions are quite different, like here. So endpoints of energy of the higher the process is the last and the lamp, so they almost occurs here. So that we can reject the higher the QED transitions, and we can distinguish the lamp signal. So all the QED background process can be distinguished with the lamp signal. If we can detect the lamp from the such a condensate atom, then we can control the neutrino physics by using the atomic system in the laboratory environment. To be specific, we can calculate the lamp signal as with energy dependence and some of the including the information of the neutrino mass. The amplitude, the S matrix, is consists of the two parts, plus of the wave interactions for the transition from the excited state to intermediate state, and the QED transition, ion transition for the transition between the intermediate states and the ground state. And this is the S matrix. So this corresponds to the ion transitions. So this is the electric dipole moments and the external energy in here, and the density of brightest by consisting by the excited and the ground side. And this is the wave interactions. This is a neutrino current, and S is a corresponding electron spin, and the G up is the Bellamy constant from the wave interactions terms. So this is a neutrino current, and also there's a mixing structures appear, AIJs in the neutrinos current, which includes the permanence matrix for the neutrino mixing. So this corresponds to the charge current contribution from the double boson exchanges, and this comes from the neutral current contributions with the jet boson exchanges. If we consider spin sum of the neutrino currents, then this terms provides the neutrino mass term, and we can measure the absolute neutrino mass scale by using the such atomic system. So this is a realistic experimental setups. The initial stage prepared by the irradiations of the two layers, corresponding the energy for the excited and intermediate state and the intermediate ground state. So for this system, there are the two layers for this two different frequency for the gas chamber with the genomes. Then this gas chamber contains the condensed atoms, and if we irradiate these two layers, then the initial state of these atoms are prepared by these excited intermediate ground states, and other ion transitions are forbidden, and by using the detectors with some optical system like as a monochromatic to observe the wavelength, which is correspond to the energy in here. And by using the PMT, we can amplify the optical signal so that we can take the data. This is the experimental setups from also the same papers for this lamp topics. By repeating this irradiation cycle, the initial state given by the such excited ground states, especially the superposed quantum state, and there is a time dependence because there's some of the irradiation cycle. And such a time dependence can be described by the mass equation. So this is a density of brightness with the excited and the ground state basis. And there are some specific mass equations functions, and we can bind some of the equational motions. And the solutions, but for simplicity, we can define the dynamic factors theta eta. There are other density price components, but the low easy, and multiplying the external electric field, we can define the dynamical factors atas with the additional sum terms n and the omega to make the dimensionless parameters, and this eta tilde is the last under one. And when the time is larger than the nanoseconds as a symptotic limit, such a dynamical factors becomes time independent. So that we can just write this dynamical factors as a constant value. So the dynamical factors are just a constant. So the total lamp light can be separated with the two parts. Just a constant part, gamma juice, and energy-dependent part, I omega. Such omega is a spectral shape. And the overall light is the lightest with such a factors. For example, the angular momentum of the intermediate states and some of the atomic informations and the ion transition light between the atomic states, and also especially there's a number density and the volumes and the dynamic factors and the strength of observing interactions, which is called the Fermi constancy. And we can insert some values for our atomic state. In our case, the Johnson atom. So there are some specific value. We can obtain the overall light for the lamp is almost order of the 1 hertz for the given some benchmark point of the number density and the value. And such overall light of the lamp signal is extremely small. 1 hertz is extremely small. This means that it's just one photon for the 1 seconds. Such extremely weak signals of the lamp comes from the small strength of the weak interactions, this Fermi constant value. So we want to amplify the lamp signal, and the method is rather than enlarging the volumes, so we want to maintain the laboratory's environment. So which is the increase the number density by using the more condensated atoms. Next, in the remaining topics, I want to talk about the spectral shapes of the lamp signal. These spectral shapes includes the energy dependence, so that it can provide sort of the neutrino mass informations. The Bohr momentums of the neutrino pairs can be written by such a form. So the difference between the excited and ground state minus the emitted photons energy, and also about the three momentum case, this is the same. And we will start that there's a neo boost of atom, so the three momentums of the EZs are equal to the zero vector. And by using the invariant of the mass, the performance of neutrino pair should be the larger than the sum of the neutrino mass, Mi than Mj. And by using this inequality, we can make the threshold of the lamp spectrum and the point energy, omega ij's, as a function of the neutrino mass. So this epsilon is able to choose across upon to the original energy difference between the excited and the ground state. And if there's a neutrino is a massive particle, then it can provide sort of the mass shift from the original and the shift. So the points energy of the lamp spectrums are shifted by the such a neutrino masses, and the spectral shapes are proportional to the heavy stars step functions with the endpoint energy threshold. So the lamps in the specifics, the lamp spectrums, especially the spectral shapes that I omegas have such exact formula. There are some of the assumptions. The neutrinos are direct types, and the CP Barton page is equal to zeros, and the neutrino mass spectrums assumed to be the normal ordering. So we can observe that there are some of the various quantity. First of all, the heavy size type function, this gives endpoints energy, and that this AIJs correspond to the mixing structure already we saw, including the permanence matrix, and also that there are some complicated structures depending on the photons and energy omegas, and the Qs are defined like that, and also neutrino mass patterns are included in here. By using this exact formula of the spectral shape, we can class the RENP spectrum. So before that, we'll use the following standards, the parameterizations of the permanence matrix, and using the neutrino parameters from the particle data groups review. And by using this, we can find the corresponding values of the mixing structures terms AIJ scale. So this is a lamp spectrum. So we assume that the lattice neutrino mass is equal to the 0.1 electron volt here, and almost near the endpoint energy in here. So this one, and in our xenon system, the epsilons are almost 0.32 electron volt. So the half of this epsilon is almost yes. So this is the original threshold. And because there are many mixing structure AIJ scales correspond to the each neutrino mass eigenstate Mi plus Mj. So this gives us 6 threshold because Ij equal to 1, 2, 3 for the each neutrino mass eigenstate. So that there are 6 threshold 1, 2, 3, 4, 5, 6. So that this gives the neutrino mass shifts from the threshold. And by observing such a threshold, we can measure the absolute neutrino mass scale. And we assume that the lightest one is 0.1 electron volt here. So compared to the other spectrums, the LAMP spectrums has more sensitivity for the absolute neutrino mass scale. Originally, in the nucleus emissions of the neutrino, for example, the treated melodic case in the CAD-LIN experiments, the electrons energy scale is almost a kilo electron volt, and the sensitivity of the absolute neutrino mass scale also there's a endpoints energy shifted by the neutrino mass. The sensitivity is almost 1 electron volt. But the lamp case, the atomic system is the energy is almost electron volt scale, so the neutrino mass sensitivity is sub-electron volt scale. And the detections is possible by the photon spectrum, so the optical methods can be used for the neutrino physics. So there are very good advancement for the lamp signal for the neutrino mass measurement. But the disadvantage of the lamp is the lamp has a very small light, so this is not detected yet. So today I talk about the radiative emission of the neutrino pairs in the atomic system as a new approaches to the neutrino physics.